We can now establish some theory of inference. We have an IID sample, and the underlying mean is mu and the SD is sigma. And now imagine that parameter mu to be unknown, and it's something we have to estimate from our sample. We're going to call it the population mean to distinguish it from the mean of the sample that we see. And we are going to assume that this population mean is a fixed number. We might not know it, but it's fixed. It's a nail hammered into the number line somewhere, we just don't know where. We're going to use the sample to estimate that number, and a natural estimator is the sample mean. You know, for example, that it's unbiased, you know how to find its variance, and so on. You also know that if the sample size is large, then the distribution of the sample mean is roughly normal. And the center is this unknown mu, and then you have a point of inflection that's sigma over root 10, and let me go one more of these. So you have mu plus 2 sigma over root 10, and try and do the same thing on the other side. So here you have mu minus twice sigma over root 10. Now, where are these numbers coming from? They're coming from the fact that the expectation of the sample mean is the population mean for every sample size, and the SD of the sample mean is the population SD divided by square root of sample size. We've seen that before. Now, the reason I'm writing these particular numbers down is that the probability that your sample mean is in the interval mu plus or minus 2 measures of spread, that is about 95%. So the horizontal axis represents your sample mean, and so we know that the chance that your sample mean is in the interval center plus or minus 2 measures of spread, that is approximately 95%. That's just normal distribution facts. Another way of writing this is to say that if you look at the distance between the sample mean and the population mean, that distance is at most 2 measures of spread with chance 95%. It's exactly the same event, written in a slightly different way. And all we're finding over and over again is the chance that your sample mean is in this interval right here. So the second expression is symmetric in the sample mean and the population mean. Distance is symmetric after all. And so you can rewrite it. You can rewrite it equivalently as the chance that the population mean is in the random interval sample mean plus or minus 2 measures of spread. That is approximately 95%. And this is a very handy way to look at things because I'm trying to capture that unknown mu. And what I've said is that if I compute this random interval, sample mean plus or minus some constant, the sample mean is random. If I compute that random interval, then the chance that that random interval captures my mu is approximately 95%. And that random interval is called a confidence interval. So it's called an approximate 95% confidence interval. For the population mean. When you see the words confidence interval, just as in data 8, your head should say estimate. I'm trying to estimate that number. I would like to say, well, it's just whatever I saw in my sample, but I know that the sample could have come out differently, and in which case my estimate would have been different. So I have to give myself some wiggle room. And so the way I construct my estimate is I start at my sample mean, which is my single number best guess for mu, and I add and subtract wiggle room. And in the end, the interval, therefore, is the sample mean minus 2 measures of spread to the sample mean plus 2 measures of spread. So what is random about this interval? What's random about this interval is its center. You see, you start at your guess from the sample, and then you add the same amount of wiggle room on either side. So it's the center of your interval that is random. So ahead of time, you don't know where this interval is going to fall. It's going to fall somewhere on the number line. And what we have said is that there's approximately 95% chance that the interval falls over our unknown number mu.